So, how many people know Faust, functional audio stream language? Well, good. It's nice to have either all know it or all don't know it. That's ideal. I love this language. It's really great. And here's an example for our simplest low-pass filter, our good friend, the simplest low-pass filter. I think the clearest way to write it is like this. So I'm defining a function of x, which is x plus x prime. And as you would imagine, x prime means delayed by one sample. So that's a very simple way to say it. But the funny thing about Faust is that the letter x can stand for any block diagram. So a letter is basically an expression in the language. It can be a function name, and if it's a function name, it gets replaced by its definition, and then in that, you scan for functions in that and replace. So there's all this rewriting that goes on, and then when you get down to the bottom, you've got pure Faust, and this right-hand side is not pure Faust. That's what's called syntactic sugar. Because the bottom level of Faust doesn't involve plus in this form. There are no infix operators really, and prime gets rewritten as well. So here's the lowest level of that. So all of these, every line here is equivalent. So we can go progressively like this. So I don't have to mention x. I can just say the simplest low pass consists of a wire. It's a block diagram. It's a trivial block diagram that just passes its input to its output. And then here's this infix notation which gets rewritten. And what's being summed is a delayed, so it's a block diagram followed by a unit sample delay. And then here's another way of writing the unit sample delay. You can just say mem. And this is closer to low-level Faust because the comma operator combines block diagrams in parallel. So this is the parallel combination of a trivial block diagram that just passes its input to its output and a unit sample delay called mem. And then that pair of block diagrams is concatenated in parallel by the comma operator. And then colon, it means cascade combination or series combination. And it says take all of the outputs from the previous block diagram and feed them to the next block diagram. And so this will have two outputs, right? It's got two inputs and two outputs. And so then the plus block diagram, that's a primitive built-in block diagram that has two inputs and one output. And so it is compatible. So there's no compiler error when you have a colon connecting these things. And so that's a nice way to do it. And now this one, let me show you that one actually. Faust has this nice facility of, let's see, what was that called? The simplest low pass dot DSP? Or is it simplest low pass filter dot DSP? Or is it T? Oh, it's test simplest low pass filter. What? Let's see. Let's do this one first. All right. What's wrong with this? Oh, I see. We want to just see. We don't want to feed it an impulse yet. All right. So let's just. So here is now our simplest low-pass filter compiled into C code. So Faust compiles into C++, and so the output is equal to the input plus fvec0 of 1. And you can see from this update that fvec0 of 1 is just the one sample delay of fvec0 of 0, which is the input. So this is the C++ implementation. And it's got it's a method of a class, a DSP class, that has a compute method that you give it a count, it's your block size, and you give it an array of input signals and an array of output signals, and it will get pointers to the inputs and the output. And the reason, okay, so that's your simplest low-pass filter, and there's something a little funny about it that caused it not to take an impulse. So an impulse, let's go ahead and put the impulse back in. You can express an impulse as 1 minus 1 prime, which means a unit sample delayed. So let's look at the compilation of this. So here's what's missing over here. This is a 2-input signal, and I'm feeding it one signal, and it's balking at that. So what I can do is say, well, look, let's let this start with one signal, and there's another block diagram operator which you can call fan out. So it's less than colon, and that says take the outputs of the previous block diagram and feed them to the next block diagram with copies. And so if it's 1 to many, it'll just be copied to many. If it's 2 to many, it'll be copied in an interleaving way. So there's this automatic interleaving that you get that turns out to be useful. So now that should be okay. And it's just the same thing. But now there's an impulse. And you can see the implementation of the impulse here. Now you can also now get an automatically generated block diagram from Faust. The compiler generates this scalable vector graphics file. And it is hierarchical too. So if there's something that has a definition, you can click on it and see that. And you can control the complexity, much as in PD or Max, by just giving names to things that you want to be at a higher level. So you can encapsulate an expression by just giving it a name. Define a function, and it'll look really pretty in your block diagram. But then you can click on that name, see its implementation. So that's very nice. So here is our impulse. It's just a 1 minus a delayed 1, and this 1 is a constant 1. But it's a 1 that comes on at time 0, so it's a causal step function. It's really the Heaviside unit step function, if we were going to use the double E term for it. So it's zeros at negative time, and then it turns on to 1. So if you delay it, then you'll get a step at time 1 instead of time 0. And if you subtract the delayed from the undelayed, you get an impulse. You get a 1 at time 0 and 0 everywhere else. So this is just a little cliche for 1 minus 1 prime is your cliche for an impulse in Faust. And then here is our filter. So you see the immediate term goes straight into the plus, and then there's a once delayed term, and this is a primitive, so I can't click on it, and so that's that. And then there's another form of this that is, I think, even prettier, and that is, so we have our single input coming in. It fans out into 2 inputs, and then we delay one of them. And then instead of going to a summer, we just do a fan in to a single output. So colon greater than, less than colon is a fan out with copying, and then colon greater than is a fan in with summation. So if in the case of 2 to 1, it just adds them together. So that's the equivalent operation to a summer. But I like the diagram better. So you don't have an explicit plus here, and the convention simply is that if 2 signals merge, then they're added. Just superposition holds, right? And another thing about Faust is that signal flow is always left to right, and that agrees with standard circuit theory. That's a normal thing. Most circuits are drawn that way. It's not so great for physical modeling. Physical modeling, you want things to be bidirectional. You want left and right. You want every action has an equal and opposite reaction, and you need to actually explicitly represent that. And so the circuits really do want to use bidirectional connections. But for normal virtual analog and normal signal processing and filters and oscillators and so on, Faust is fantastic. It looks really natural. Great way to digitize your circuits. All right, so now we have all these examples, and now, as I was saying, there's a lower level of MIM, and it's called AT, and it's more general. So you can say take any signal and ask for it at some delay. The delay has to be an integer. It's implemented using a delay line. It automatically finds the bound on the delay that you ask for and gives you a delay line that's large enough to accommodate that. It even finds the next power of 2 so that you can implement the delay line very efficiently using address index masking. But as I said, this infix operation is a syntactic sugar. So the way it really looks in the lowest level of Faust is like this, where your input signal comes in, it fans out into a straight through path, and then we need parentheses here to get the parsing to be correct, because this block diagram consists of an input and a number, the number 1, And those two signals flow into the at operator, which is a built-in operator that has two inputs and one output, very much like plus, but one of its inputs is the amount of delay, and the output is the other signal delayed. But everything's a signal, or really more generally, everything is a block diagram. But built in things like 1, it's a block diagram that generates an output signal consisting of 1, 1, 1, 1, 1, starting at time 0. And it has no inputs. So it's even little constants like that are properly understood as block diagrams. They're just synthesizer block diagrams. Okay, and then that is the same thing, and then we fan it in, and let's just test it to make sure it works. So you test it by first saying Faust and see if it compiles, and then you say Faust to Firefox and look at your block diagram, and if it looks right, it's probably right. And normally you don't even look at the C++, at least I never do. Only if I've got some really obscure problem will I go into the C++. 90% of the time and more, I do what I just did. I compile it, make sure there are no syntax errors, and then I go Faust to Firefox to look at the block diagram, check it out, and then it just works. And now I can say Faust to VST, make a VST plugin out of this thing, or I can say Faust to AU, make an AU plugin. I can say Faust to Jack, make a standalone Jack application. I can go Faust to PD. I can go Faust to Max MSP. You can go Faust to Super Collider. I honestly don't think there's any major thing missing now. The ability to cross-compile, because everything's C++, right? And so the way that you get to these other architectures is by means of architecture files. So for example, like one of my favorite actually is Faust to S&D, I think it is. Let's see if I've got that defined. So let's just cat that. What it does is call Faust with, this is stuff that I inherited from these scripts in the distribution that are generalized. In Faust, you don't have any, what are they called, auto tools. So you don't do a configure and a make. You don't use any of the cross-platform adaptation tools. You just say make, and all of the detection of platform, which is Mac, Linux, and Windows, all of that detection happens in the make file. I consider that very cool, actually, because I'm very comfortable with make, but I'm not comfortable with generating config files for configure. It's just, I find it really a pain. Some of them are better. The Python stuff is pretty good, but doing it in the makefile is very cool if you can get away with it, if it works. So the active ingredient here is this one line. Where is it? Let's find Faust-A. This is it. So you say Faust compiler, and you give it a -A argument, which is the architecture file to use. And so there's a architecture file, sndfile.cpp, and you can go find that and see what it is, and you see that it's basically a wrapper in C++, and it pulls in what you need, which is in this case, where is it? S&D file, yeah. So this is the key line here that pulls in sndfile.h. That's the the lib S&D file stuff, and it's very useful for making a little standalone program that that will run in the command line. And let's look at main. So it has a little main program, and so it will generate any number of inputs and outputs from your Faust patch and map them all to sound files. So I use this to just do sound file processing, and it opens the input files, the output files, and then it calls the initialization for the DSP class, and then the interface is another class for all the GUI stuff, sliders and stuff. And those you can actually control a bit from the arguments. And then it goes across all the blocks and calls the compute loop. So this is just an example of an architecture file, maybe the simplest architecture file that just, because there's almost no GUI stuff. But if you look at something more complicated like Faust to Jack, what is it, like Jack? There's the console app, that would be the simple case. But you see GTK and Qt. So in the Linux machines, I would say GTK is the more native choice of GNOME toolkit, And, but you can also use the Qt or Qt toolkit. And so in here you'll have a lot more stuff pulled in, but a lot of that's been generalized into a subdirectory of GUI related stuff. And you can control this stuff from OSC, which is nice, and there's an HTTP version. You can compile this stuff for running in the browser. And so here's the main, and it builds a bunch of stuff. And yeah, so architecture files can get complicated, but the net result is you can say Faust to platform and Faust to plugin format, and it just works. And so if you want, you can just avoid architecture files, just use them, and from your point of view, it's just Faust to anywhere, and life is good. All right, so we can do that, but let's get back to the example, and yeah, I don't know, why not just go ahead and do that. Faust to S&D, what was it called? Test simplest low pass filter.dsp. And so it should, oh, I don't have something. All right, so this is when you have to actually look at the C++. Oh, Clang failed. Oh, you know what? It's using the wrong compiler, I think. All right, let's go Faust to AU. Input file does not exist? What? Did it kill my input file? That's crazy. That does not normally happen. It is gone. That's crazy. Well, I've got a buffer here in Emacs. Good reason to stay in Emacs. So that's a bug, man. I'm going to go after that one tonight. You don't allow bugs that kill your input file to live very long. All right, so Faust to AU, that'll generate an AU plugin for Logic. And that's done. But let's do it manually in order to see the code that's produced. So what is it called? I think it's just AU maybe. Maybe it's in a subdirectory. Oh, there it is, au.cpp. So it's a CPP file always of test simplest low pass filter.dsp. And there it is. So the compute loop looks the same, but what's different is all the setup. So there's all this Mac OS API associated with AU plugins that's been generated. And this is all in the architecture file. The architecture file has little hooks in it for the generated Faust code to get plugged in. So there's like an initialization area, and then there's a compute area. And so that's all. Some people call this programming patterns. So the architecture files are like programming patterns. All right. So hopefully I didn't belabor that too much. But I guess what this is a sales pitch. I want you to see that, hey, you know, if I port my stuff to Faust, I've ported it to everything. I'm done. And the only real question you want to ask then is it efficient? And the answer is quite efficient. In general, it's usually within a factor of 2 of a hand-optimized, carefully written C++ program. It's very difficult to beat the Faust compiler. And one of the reasons for that is that it takes the expression and puts it in a sort of binary tree normal form, which is called block diagram normal form. And in that normal form, it can discover identical computations. So it will automatically discover and reuse computations. So sub-expressions that are needed in more than one place get computed only once. And when that works perfectly, you can get the FFT algorithm to fall out. All right, so this will now generate an impulse into our simplest low-pass filter. Now I want to show you some of the tools for evaluating this stuff. So let's first do a Faust to plot. I have aliases for everything, so to show you the full form, I have to look at what it is expanded to. So I should say Faust to plot of tslp.dsp. All right, so now it has created a program that will simply print. So I can now run tslp, and there is the impulse response. And we all know the impulse response of the simplest low pass, and that's it. And you can see that it's written in a form that is ready to be digested by MATLAB. So it will put this impulse response in the variable Faust out, and it will plot it. And it'll give you a title and a label. So it just kind of helps you along there. And there's a faster version, Faust to Octave, that basically uses Faust to plot and then calls Octave. And so here we are in octave, and I have to find the figure that it generated. So this is now the impulse response. It's hard to see because it's just 1, 1 right at the origin there. This is stuff I'm going to show you in a minute. Let's not give it away. So now, so we have this variable Faust out. Let's look at the first 5 elements. So there's our impulse response. What's more interesting is to plot the frequency response. So now I can say plot the absolute value of the FFT of Faust out, and I can give the FFT any size I want, so maybe I'll make it 1024. Normally we don't want to see the whole thing. We just want to see the positive frequencies. In octave, you can index the output of this function. I don't think you can do this in MATLAB, not the last time I tried. So in MATLAB, you have to write this out in 2 lines. First, you get the FFT, and then you index it from 1 to 512. So then you can plot the absolute value like we often do. And there's our good friend, the frequency response, the amplitude response of the simplest low pass, gain 2 at DC, gain 0 at half the sampling rate. Oh, here's one. Do you know this one? Axis tight. You can say axis tight, and it'll get rid of that little excess over there. So now the axis really goes from 0 to 512 or 511 and 0 to 2. So there's our simplest low pass. So next I want to do some Butterworth filters. Let's see if I did everything I wanted to do. Let's see. Yeah. That's good. So we're ready now for the Butterworth filter, test Butterworth. Now this one I'm going to grab 2 things out of the library music320. Now in a lot of Faust code you'll see it like this. It'll be an import, and then that'll pull everything in at the global scope. But I've taken to not doing that anymore. I like to keep the scope separate. So if I say ml equals library of music.lib, then that whole namespace gets attached to the ml object or function. Everything's a function really. And then ml.pi is the variable pi in that namespace. So I'm going to use pi, and I'm going to use the sampling rate. I mean, I could have defined pi, but defining the sampling rate is a little tricky because that gets set at runtime by the system. So the expression for that is a little bit hairy. So, and I'm also changing the notation to what I like to see. It looks more like MATLAB. Okay, so now this is the, let's see, what is this? Yeah, here's the line we want to focus on. I thought I got rid of this actually. So the parent, oh yeah, okay, no, this is okay. I did, this is actually what's in the Faust library. So in the Faust library, filter.lib, you can find all of these functions such as low pass, high pass. But it's a little bit hairier because I've unified low pass and high pass. And so it makes the code not easy to read. So there's this variable s here that is 0 for low pass and 1 for high pass. And so to make it a little more clear, I've basically copied out this code and gotten rid of the s variable. But I still have a parity variable, which is whether, you know, the parity of n, or n over 2. So is n even or is it odd? And so I set the parity to n mod 2. So it'll be 0 for even and odd and 1 for odd. And then I construct this s variable, which is the section number, as O minus the parity over 2, where O is the order. So note the difference between O and 0. So here is O, that stands for order. Here is 0, which is 0. All right, so here's the definition of a low pass, a Butterworth low pass of order n and cutoff frequency f sub c. So it's defined as this function, which has this name space definition. So a with block basically says define everything up to the next curly brace as a context that only is seen here. So you can think of it as a function body. So it's a function definition with a scope in which it's defined. And so that function so the LPR function is defined as this. Now this is using pattern matching. Pattern matching is a facility in the Faust language that allows you to define things recursively. So here's how it works. So LPR of 0, n, FC is defined as a wire. And so the way to think about it is it's the order 0 case. Okay? So for order 0, we just want a wire. What else can we do, right? Now, order 1 is defined as a first order transfer function. And the S means that it's an S-plane transfer function. So it's a transfer function, order 1, in the S-plane. And so that means these coefficients are in the S-plane. And so the coefficients are 1 for the numerator, and for the denominator, it's also 1. It's a pole at S equals minus 1, because this is 1 over S plus 1. And then the last argument here is the frequency scaling variable. So it moves omega 1 to whatever omega you give here. So this is how you set the cutoff frequency by means of frequency scaling. And you might ask, well, how can you implement this in the S-plane? This is a digital filter. Well, lo and behold, let's go look at its definition. TF1S is defined as a first-order digital filter whose coefficients are B0D, B1D, A1D. So it's got a it's B0D plus B1D Z inverse over 1 plus A1D Z inverse. So it's your basic first-order Z-plane filter. But we've got to compute it from the S-plane coefficients and frequency scaling value. So we've got B1, B0, and A0 for coefficients, and omega 1 is our scaling factor. And here it is. This is the bilinear transform. We all know about the bilinear transform. If you crank out the algebra, this is what you'll get for the first order case. And the only tricky thing here is that the constant in the bilinear transform is tuned to match the cutoff frequency exactly. So omega equals 1 is used as the exact mapping frequency. So remember, the bilinear transform exactly maps DC to DC and infinite analog frequency to half the sampling rate in the digital case. And then you have one more degree of freedom. You can map one more frequency exactly. And normally that's the neighborhood of DC, which gives you C equals 2 over T, or 2 times the sampling rate. Here, you're matching exactly the 3 dB point of the filter. So it makes it an exact spec preserving mapping for low-pass filters. And if you do the algebra, you'll get this. You'll get 1 over tangent. If you don't get this, let me know and I'll fix it. I can fix anything in the Faust tree. But this has all been tested, and you'll see it. I'm going to test it right in front of you in the next minute that I have. So, so that's it. And this all kind of looks more like Fortran, right? So this is all that syntactic sugar making things pretty. But really, D is a block diagram, C is a block diagram, plus is rewritten. You know, it actually all rewrites down to that low-level Faust stuff that I showed you, right? But you can also kind of write it as Fortran or you know, high-level C++. So now you get the idea. So we can actually specify a filter. So the Butterworth filter has its poles specified in the S-plane, and then it goes through a bilinear transform into a digital filter. So this is how we call it, and it just does it. Now we go through this pattern matching. So if it's order 0, we catch it here. If it's order 1, we catch it here. If it's a general order, then we decrement the order by 2 and call this thing recursively. And then after decrementing it by 2, we go into a second order S-plane transfer function. Same story as the first order, but it's second order, so it's a little more stuff. It's same algebra principles. And then we have the parity computation, which gets into the poles. Remember that for an even order, we have to do this rotation of the poles. But really, you can see it's a pretty darn simple thing. You know, we just have the closed form location of the poles, and they're in the S-plane, and then we run it through a bilinear transform. Here's what it looks like for the second order case. It takes you from an S-plane biquad to a Z-plane biquad, matching the normalized frequency of the minus 3 dB point exactly. And then here's the implementation of the first order transfer function in the digital domain, and it's just standard Faust, right? You have an input, you fan it out into a multiplication by B0. This is a new construct, times of coefficient. That rewrites into, input, comma, coefficient, colon, asterisk. But it's more syntactic sugar. And then you go through a delay and multiply by B1, and then you add those together, and then you also have this feedback. And this is a new thing. Tilde is the feedback operator in Faust. It says feedback through the following block diagram to the input, to the first available input to the left. And I don't think you need this 0 anymore, but there was a time when you did. I won't take it out now. And then that's the first order case. The second order case is implemented using IIR, which is given here, and IIR is a subtractor with a feedback through an FIR filter, and then all that in cascade with an FIR filter. And here's the subtractor definition. It's just for making it prettier to write down. None of this ever has any impact on the computational complexity. All these functions get compiled away and minimized, so you can make as many pretty names as you want, and it'll all boil down to the same computation. And then here's the definition of FIR, also recursively defined as multiplication by a coefficient, and then everything in parallel, which is then recursively. I won't dwell on this. You'll probably have to stare at this for a while, but this is another recursive definition of the filter using pattern matching and recursion. And so if it's just one, if it's an FIR filter of order 0, meaning one gain, it's just a multiply. So finally, we can now give this impulse and just pick a coefficient, a cutoff frequency. I'm picking 10 kilohertz because that's halfway up the bandwidth, so that'll be halfway to Nyquist limit. And then we'll have the process be an impulse into a parallel combination of, well, let's keep it simple for starters. We'll just say, whoops, what did not happen there? So let's just go to one of them. So let's go to a low pass of order 3, just as an example. And then maybe we'll do a low pass of order 12 to give a bigger one. And then I can show you a bunch of them. The PAR construct says for I equals 0 to 11, make all these different low pass filters of all these different orders. So let's try Faust of test Butterworth.dsp. So it compiles, that's good. Now we can look at the block diagram. There's our impulse. See how the names occupy the blocks. So the third order low pass consists of a first order S-plane biquad followed by a second order S-plane. So we get our biquad realization just all for free, and we can get down into this first order transfer. And what you see are the coefficients in the digital filter, but the digital filter coefficients are computed using the bilinear transform. So you see the 1 minus C over D. So the bilinear transform is embedded in this digital filter coefficient. And you might think, well, gee, isn't this really going to take a lot of time because I'm doing a bilinear transform every sample? Well, only if you put a knob on it. So in Faust, if you don't put a knob, then it will all compile away. So if it's a constant, this is another great thing about the optimization. So the actual computation is minimized. It's just like you would do in C++ for a fixed thing. But now what I can do is come in here and say, I want this cutoff frequency to be a variable. I want to make a VCF. So I'm going to say it's a slider, and it's going to be called cutoff frequency, and it will default to 10,000, but it will be variable from 20 to 20,000, and I'll allow steps of 1 hertz. For historical reasons, there's an increment, and most of the time that's ignored. That's the step resolution. Some plugin formats require that. So now I've got a GUI, right? And so let's see if it compiles. Yes, it compiles. Now let's make a Faust 2 core audio application. That's kind of a standalone thing. I don't have to run Jack. That's just a Mac standalone thing. And now let's open it. And, oops, not the DSP file, the app, please. And so look at that. I've got a filter, and the input is coming from the microphone. Oh no, it's got an impulse, sorry. So there's no input. Probably a good thing, because it would probably be feeding back right now, because the microphone input would be going through the filter, and that would be coming out my speakers and going back in the mic. But now you see I've got a wire, a knob. And this knob is controlling the analog frequency cutoff, which then does go through the real-time bilinear transform calculations to make it a digital filter. And so it's really very nice virtual analog design. So it's a good thing. And if I want to smooth it, I want to get rid of zipper noise, I can take the slider and run it through a smoother. And this is a one-pole filter, 0.999. And now when I move that around, it won't make terrible noise. And let's go ahead and get dangerous here. Let's put noise times 0.1 into a low pass and see if we can hear that. So we make it. Hello? You don't have noise. Well, I thought I imported music.lib. Oh, right. So I have to call it music library, music.lib.noise. I've encapsulated that in that namespace. So now, what's missing? Smooth. Smooth is in the filter library. So I'll just import filter.lib. I mean, it's just a one pole. I could just write it, but let's just see that. Now what's missing? Huh? Well, we're out of time. Well, let's see. It's on line 3. What did I do? Line 3. ML equals that. Oh, missing semicolon. All right. So now we have multiple definitions. Filter library equals library of filter. Yeah, I did have collisions. Absolutely, I have collisions on that. And now smooth will be filter library.smooth. And what could go wrong? How many bugs can you get in 5 characters? Okay, so and let's open it. Yeah, you hear that? Low pass, smooth, no zipper noise. Very nice. So so that's it. So I'm out of time, but next time I will then go into the MATLAB stuff. There's a lot of nice MATLAB tools for looking at filters. But this was a good first look at Faust tools and stuff that's in Faust that you now understand and can use. So if you use the low pass function, you know it's a Butterworth, you know where the poles are, you know what its characteristics are. So understanding what's in the available libraries is kind of the name of the game these days.